So what does any of that have to do with annuities? Let's get back to it. So returning back to annuities, one of the points that I think is important to make is that the annuity is really a geometric series. It's a sum of a bunch of things. Like for every month, our current balance is multiplied by a percentage, or our payments multiplied by a particular percentage. And every month it's by another percentage in that sort of formula for the present value of an annuity. So it's a geometric series because each month is just another multiple of by 1 plus the periodic interest rate. Or really it's being divided, but same difference is being multiplied by 1 plus p to the minus 1. So basically this formula can be applied to find its sum. That is the summary. And now let's go ahead and do that. So looking at the annuity, and I've fixed it on this slide because I messed it up on the previous one as I stated uh, in, the prior video. But basically, if we are trying to find the sum of an annuity, since this is a geometric series, we could use the formula for adding up a geometric series, which will always be governed by the formula a times 1 minus r to the n over 1 minus r. And basically, in this case, a is the first term, n is the number of terms, and r is the common ratio. So really, the formula, while all this seems really complex, is quite simple. I plug in the first term, which was just r times 1 plus p to the minus 1. I plug in the common ratio, which, because each term was multiplied by 1 plus p to the minus 1, it's 1 plus p to the minus 1 is r. And in here, it's not it's 1 plus p to the minus n, because r is exponentiated by the number of terms, which was just our generic n to begin with. So basically, this will give, or not so basically, will give us the formula, the sum of the future value of an annuity. And it turns out there's an awesomely neat way to simplify this, which is on the next slide. So if we take that big hell of a formula, since 1 plus p to the minus 1 is a negative exponent, we could drop that down to the bottom, which is what I did in this next step, which would change it to a positive 1 exponent, which is just would disappear. And then if we distribute that through, or FOIL it out really, what I would get is 1 plus p times 1 and 1 plus p times 1 plus p to the minus 1. And what you might notice about 1 plus p times 1 plus p to the minus 1 is this is 1 plus p divided by 1 plus p, which cancels out to make 1, which is why this yields 1 plus p minus 1, because really it's 1 plus p divided by 1 plus p, and it's minus that whole fraction. And in the slides, I didn't show every little bit of algebraics. That's the point of the video. And on the top, I have my r, which to review was the payment for each of the annuities, or each of the installment amounts. And then I'm left with 1 plus p to the minus n. And this leads us to our final formula for an annuity, for the present value of an annuity, which is the net present value. So this will give us, going back to the prior diagram, the sum of all of those payments. Basically, if I'm imagining Johnny paying $200 every month to the bank with getting a particular interest rate, I could predict how much that's worth today by finding that present value, and that's exactly what we'd be calculating as we do this. In the next video, I'm going to move to the packet, and we're going to do some examples of actually solving some stuff, since we haven't done any annuity examples yet. And I'll discuss this formula, which is also present in the packet, and try to describe the finance notation, which is fairly unique.